here, and it's behaving the way the moon does. So we have another issue here. So a lot of things he's finding here. So Galileo's figuring out these things aren't perfect. The moon is potted. The sun has spots. Things are the moons are going around Jupiter, not around the Earth in little crazy little circles. They're going around the moon. And then he's got Venus that is coming up as an imperfect, it's not spherical. But it does show that eventually you do see it. It does go spherical when it's back behind the sun and it's getting a full reflection off of it. But it shows phases like the moon. And that would only happen, well, I say it only happened. It should only happen. I wanted to say it only happens if it goes around the sun. Not necessarily true, but the way the shadows do form on Venus suggests would prove that it does. So even if you have a Ptolemaic system where Venus is going around the Earth and the sun's going around the Earth, you would expect to see shadows from phase, but not the same way as if everything's going around the sun. There's a slight difference there. So that's part of the problems. So let's see. And so we run down through here. Yeah. So what Ptolemy did to try to make this fix all this was use epicycles. But even in the epicycle, you have the deferent, which goes around the Earth. Everything was always going around the Earth. So it just breaks down. Okay. And Venus's epicycle, that is the thing. If you really look at the position of Venus as it goes around the sun, then you run into troubles because the epicycles, they just break down. And for about 1500 years, the astronomers were amazing that they were making this work by doing epicycles, even on epicycles. And I remember going to, if you ever get a chance, to go to Chicago, go to the Adler Planetarium, and back in the day, they had these huge orreries, which were basically clockworked representations of the solar system they had one that had the Earth in the middle, and they had little epicircles trying to make everything else work. Just an amazing device. It just doesn't work. All right, but Venus was really a telltale that what should have happened if the so here we got a nice cycle, nice image here. If the Venus has epicycles and it's going around the Earth and the Sun, then we should never see a full Venus. It should never happen. It should never go full. The only way that could happen is if Venus goes behind the sun because it's reflecting the light from the sun towards us. And we do see that. And so, yeah, so sorry, Ptolemy, you've lost this one in a big way. Venus alone really shows that Venus is going around the sun. It's not going around us. And then you got to really rethink things a little bit as that happens. So I know Professor Dan really goes in detail about this, and there's some really neat things about the phase and angular diameter transitions and things. So if you look at the position as it moves, you can really prove this out as far as the two. So here's a heliocentric system, and you can see the phases that you would normally expect to see with the heliocentric system, and that's what we see. And we go back up again, we compare that to a geocentric system, not the same. And if this is putting Venus closer between us and the sun, if you put Venus outside the sun, it still doesn't work. So that doesn't fix it either. And they did know enough to know that Venus was closer to us than the sun was. Interesting enough. I'm not sure if all Greeks would have agreed to that because they put the sun at about 200 miles out at one time and the moon at about 100. So probably a little bit of differentiation there. All right. So if we look at the difference between a heliocentric model of the universe and geocentric models, and you look at the phases as Venus transitions, um, it just doesn't work. What we model, what we see, will fit the heliocentric model. Okay. So keep going forward. So this is a fun exercise, and I don't know that I ever did this with you guys with the string. And do we do a rope and two people holding onto the rope?
No, I don't think we did.
All right. You most years I try to do something like that. It's kind of fun to do because you know an ellipse has two focal points. So if you take a string and a pin, or you take two people and have them hold ropes, you can do an orbit. If the people are right next to each other holding the ropes, then what shape would you get?
You'd get a circle.
Exactly. So eccentricity changes as the people move away. And if you go far enough away, it breaks down at some point, right? The ellipse will break down. And that leads us to the next shape. So the orbits of planets, Kepler showed that the planets orbiting the sun are not in circles, but they're ellipses. I would go so far as to say Kepler went a step further too. He showed us that all objects in the solar systems, they all travel on conical shapes. So when you slice a cone, and I think it's farther down we go into this, that all objects in our solar system behave according to some kind of a conical shape. For us, like on the Earth, it's a very close to a circle, elliptical orbit, very close to a circle. We have ones like Pluto, which is not a planet, but is extremely eccentric. You've got Mercury, which if I had to bet money, I'd say in a few years we lose Mercury. It's a very eccentric path also. It comes close, goes away. It's got a lock to the sun, but then it's rotating. I think it's going to turn into a ring. I think we'll lose it someday. This is a guy, Kepler, who was doing these calculations without a calculator, probably without an abacus. This guy just was really good at math. And how he was trained in high school was not with calculus, I believe. And it wasn't so much algebraic. It was algebraic, but he was trained trig. He was trained in conical shapes, which is why I think this resonated so well with him, which it had to be like the worst way to ever learn mathematics. I'd pick any other option. I'll pull my teeth out first, okay? That would be the worst way to learn it. But he knew it. And so he could do the big calculations. And the big aha moment was he realized there's a relationship between the distance, which here is labeled A, and how much time it goes around. And it's a squared to cubed relationship. And he could confirm this. So, Ron, you remember who he visited? Who is the guy, the jerk who he visited on the island up in Copenhagen? Start with
Uh,
a B.
the
Tycho.
Tycho Brahe.
Brahe, yes. So Brahe had his island, ruthless guy, would beat his peasants to take incredible observations. So he had great data. And Kepler was using this data to show that this model worked. Brahe had a different model he was using, which is weird. Everybody agrees it's weird. Not geocentric, not solar centric. It was based on the second focal point of an ellipse. I'm not going to get into that, right? It was just weird, okay? And Kepler pretty quick figured out he was wrong. And he probably kept himself, probably mum was the word, probably kept really quiet because he wanted to prove the Copernican model, and then better than that, his own model, that it was, we had elliptical orbits, with conical shaped orbits, that everything moved around the sun in conical orbits. So the bigger equation, you've seen this before, 4 pi squared over gm. G is your universal gravitational constant, and mass. And what he figured out was you can cheat by using units of years in astronomical units, right? Because if you do that, then you get one, and you get one, and this is a constant. And the way that could be work is for this all to be basically one. You could work this out. You call this constant G, whatever you wanted to call it. So he worked this out, and he ends up getting a simple relationship. Now, what I didn't do last year is what we're seeing here is, all right, so I got 4 pi squared GM, okay? So if you work down through this, if you look at the period per year and the distance per AU for the planets, you can actually relate a solar mass to the mass of the planet. Now, this is a new one. And so this is our ticket on this one to do some real damage. Not a relationship I usually share because it's like one more thing for us to learn. But for us in this course, we can do it. We can take a look at it. So it's a very simple relationship here, thankfully, because we know that part of it comes out to be one, right? But if we look at the distance to period using the distance in AUs, period in years, this cube to square relationship will solve for the mass of the central body, is what we get here. It's kind of a neat way. So you can measure the semi-major axis of a moon's orbit around a planet in AUs and orbital years, and that will give you the mass of the planet. How are you doing? Okay? Making sense?
Yes. Just
Okay.
just manipulate it. Just move the things around.
Yeah, it's quite a manipulation. See what we're doing here is normally you would go through this process, and for the mass, you'd put the mass of like Jupiter in here and the universal gravitational constant, and then you can relate the distance in like meters to time in seconds and work it all out. But this is actually kind of clever. By leaving the solar mass in there and using AUs and years, we're relating everything back to the sun. So we can look at something in terms of like moons going around a planet and look at the distance they are in terms of AUs, look at the time that they have in terms of years, and then this relationship would actually give us a object's mass in our solar system in terms of solar masses. You jive? Does that make sense? You buy that? Well, good. I sell things well. All right. So, what kind of object in our solar system be worth trying to do this with? Who's big enough to reduce our errors?
Jupiter.
Jupiter, there we go. So that's why it's nice to be able to have SkyNet where we can image these things and we can actually try to use Jupiter's mass in here. Well, no, Jupiter's the distance and the period for an object going around Jupiter, one of its moons. We can take a shot at getting the mass of Jupiter, which is amazing. You know, the fact that we can actually determine the mass of Jupiter here. So the next procedure is basically taking you through this. We're very lucky because Jupiter and Saturn, since actually any of these we could use, Jupiter, Saturn, Uranus, and Neptune. And of these four, do you know which four are actually in the sky right now? Not close to the sun?
I think that Uranus and Neptune are visible right now, and one of Jupiter or Saturn is visible.
I think they're all up. I think we're really lucky. I think at least three out of the four we can get right now. Jupiter's coming up really late ahead of the sun, which is good, and Saturn is very late after the sun. So those two, I think we could definitely get. And I just imaged it was either Uranus or Neptune, and it came through pretty good too with the moons. So I think we almost we may have lost one to the sun. They used to be Uranus and Neptune right by each other, but I think we might be able to see all four. So maximum sun elevation, -12 was enough. I've been doing a little bit more than that. Minimum target elevation 20. I think that'll allow us to see everything. Visible hours. Now we took this down to half an hour is what he did. That's enough to get your images of these things, I think, pretty quick. It's only 1 second. And we select the planetary system, check the observability chart, and then here's the filters reminding us how these go. So I would highlight these and I would drop these quickly in the chat. So we have those, and that's the values we'd want to set up to make this work. Make sure you do generic 12 or 16 inch or prompt 5 assist, but I would do generic 16 inch. And you're okay doing the SkyNet now, right? If I'm good about that. So you know the drill. I did have bad luck a couple weeks ago at Jupiter, but then I did one Monday and I had it done by Wednesday. So the turnaround's been pretty good. I think the weather was is better or has been bad down south. I was doing off the Chilean mountains. They may have some issues. Everything looks to
For
be up here. Okay, under
whatever
advanced.
reason, my Jupiter observations just won't go through. They're still buffering.
Oh, so the old ones, I canceled my old ones. I started over and they went right through. It took about a night or two. Okay. Now, what this is new. This is new. We're going to use advanced options to do this. So we've been skipping that. We're going to do to hit sequential filters, but we're going to do this. Continue on next available telescope if interrupted. I've been sticking with the same one, but when I did this, I had good luck. So this is up to you. Abbas, I don't know how you feel about that, but I kind of like using the same telescope for multiple frames.
Yeah, that's also depended on many different things, but this specifically on the top of the mountain telescopes might be better chances that we have on this sequential. Well, also depended, the because we do it as 14 days, 2 weeks, and every day apart. That's the chances on any single place in the world that all of them is good weather condition is might be not possible. But I think the option that we have here is sequential filter and also continuous on the next available telescope captured. But when you're choosing that one, normally I try to choose the one on the top of the mountains, like a
Mhm.
Chile or, for example, on the Poland. Poland also, the telescope on the Poland is better. But if I choose one of them on the, for example, Chapel Hill, might be very difficult because we're mostly cloudy and rainy, and it may takes longer. But based on my experience, is that is next available, but the one that we're choosing, the telescopes, we're choosing the right one that has more capability and chances to get the things. But uh, if we take it all exposure on the same telescope, it little bit chances very slim. And the other option is that run on multiple telescope at once, and that's going to be very difficult also. I
Mm.
think the one that is chosen here is more chances to get succeed, but it doesn't mean that after 2 weeks we're going to have all the results. And because of that, we have to start this one as early as possible and choose the right telescopes. That's my own insight. What do you think, John, on that?
Yeah, it makes a lot of sense. Especially I forgot when we go in, we get to pick which telescopes we want to pick from. And
Yeah.
if you
But
pick the
based
better
on your
ones, you can do
yeah,
that.
based on your experience, what you find out?
Yeah, that's probably not a bad idea. Plus, sometimes when it does hop around the telescopes, you may lose one day. Sometimes,
Yeah,
like the moons are off the frame. You got the planet, but the moons are off the frame. And if you lose one day, it's not in the world. It's when you lose all of them that's a problem. So I guess there could be some good advantages to that too. But this is where we're going to repeat the observation 14 times, at least a day apart, and cancel observation. I'm not sure if we did. I don't think I see it checked, but these are the main ones we want to do. And I did for fun, in case you're curious, Ron, I did actually do this in like 3 hour intervals also, and just to see the movement of it, because you make like a GIF of it, and you could also use that to determine the same thing. But this will give us good data. So what we do with this then is we when you pull this up, we'll be looking in Stellarium to see which moon it is. So you need to have UTC time from the information, and you also need to in Stellarium go to Greenwich Observatory. So you're at 0 UTC, and then everything's very easy. You could try to translate it here in Charlotte area, but it's a bit of a pain. It's easier just go to Greenwich and then figure out what moon is up at that time. And the moons are listed here: Jupiter's Ganymede, Saturn's Titan, Uranus use Oberon, and Neptune is Triton. And these last two, you'd think that one's popping out, but they actually have multiple moons too, and it's not obvious which one's which. So Stellarium does a really good job of showing you when you zoom in what moons are where, which works really good. Um, so make sure you record the Julian date the image was taken in the table below. It's the nearest zero point 0.1 days. That's a dating system that's goes way back that we trust. Um, and it avoids a lot of the issues like leap years and all that kind of stuff. Adjust the brightness and contrast, and we zoom, we can show how to do that. So you can actually see the moons, and that's actually really fun. I can show you that. And Stellarium to define which one is which. If it's too close to plant to see or so far out, skip the observation. Yeah. So if you're not sure, it's better probably just to skip than use it. And I've also often always watched for shadows on the moon. If it seems like the moon's not there, it might be going across it. Sometimes you see a black shadow going across the moon, the planet, which is kind of cool. You want to do is want to measure the angular separation between the center of the moon and the center of the planet and record that to zero point 0.1 arc seconds in the table. And here's our table then, Julian date, angular separation. And I'm just kind of going through the math side of things. And you get all that in there. Then I believe Astromancer is coming up pretty soon on this, so we can work this out. All right, so the website we go to, that's got to be, yeah, it's Astromancer is where we're going to. So I'm not going to open that yet. I want to go actually to SkyNet if I can.
Mr.
And
Taylor,
yeah,
so the repeated 14 measurements that across the 14 days, that will get us like all the data we need for the moons, correct?
it will, it should. Yeah, what you're going to see in Astromancer is it will do a plot like this, and you'll match it up. Um, I mean, you have a lot of credits. If you want to run it twice, what I would do is do like they say, one a day for so many days. And this will take a while to get your data. But you might also try, if it's Jupiter, you could do like every 2 hours for 2 or 3 days and probably get really good data. That would make a nice match to your curve. I'm trying to think what the period of Ganny is. I don't think it's very long. I think it's a pretty quick trip. You know what? Since I'm asking the question, I don't know what the book value is. So period of Ganymede is about 7 days. So even with a couple of 2 or 3 days, you're going to get it. You're going to get part of that arch. You're going to see it kind of going. So I guess 7 days is probably the minimum. 3.5 days, 4 days would be a minimum to get a decent curve on that. But it should be able to get something, at least one nice bump on this. This one actually works pretty good though. Astromancer is an amazing program for trying to fit this data. It's a little bit of guess and check. I personally think one a day for Jupiter maybe is too much time. It makes it a little tougher to match. For Uranus and Neptune, this probably makes a lot of sense. Okay. Um,
And also one thing, you is better. For example, if you start the recording, for example, you hit one picture, second picture, third picture, you can start developing collecting the data, and then you see the how it better. Normally, 14 days. If you get the graph by 8 days, and that's a good investigation also. When you get 6 or 7 and see how the graph looks and orbit values. Then you get the 9 and 10 and 11 and 14. As you see it more numbers, you get more accurate result than the things that you needed.
That's a really good point. I forgot about that because as soon as you get them coming in, you don't have to wait for all 14 to start plotting these out, which is really cool. So I'm gonna go ahead and there it is. There is Jupiter. The things
Very
that you'll want to
beautiful.
do. Looks nice, doesn't it?
Yeah,
It came out
yeah.
nice. I may have played with it already. I think it came in like this.
Oh,
And when I took the images, this is the image of Jupiter set for the moon settings. I did it also without the moon settings, and it looks about the same. They're pretty close. But you can see the moons, right? You can see the moons in there.
Yes. This is what you were editing at lunch, I recall.
Oh, you saw that. Okay, I'm gonna go back to the other one though with the moons, which is kind of fun. And so this is where we can adjust things like our saturation levels are really handy to use for this. That's the default. If you do bright target, I mean there it is. And I was amazed the spots there. We have the great red spot is back. Haven't seen that for a while, so I was kind of glad to
oh,
see if I
very
can zoom.
good. I can see it.
Yeah, you see it? Isn't that amazing?
Yeah.
I thought it was gone. I thought it was gone for good. I thought they were saying it was going to go away, but that is looking really good. So we're
That's
not the only
also
ones having
it's
hurricanes.
yeah. That's also is very very. If you put for example, entire Earth surface over there, it's gonna be very small on the. I forgot the sizes, but it seems to be inside the red spot. We can put many Earths inside.
It's
I'm
huge,
not sure.
huge
I have to
hurricane.
check. Yeah.
Now, at this point, we can't see the moons unless now there's a possibility that was a shadow of a moon, but I don't think so because I saw another one and it looks like it's still there. So I'm thinking that now that better not be the moon, a moon shadow, or I'd be kind of upset thinking that is a great spot. But I'm seeing a bulge right there, so I'm pretty confident that's what that is. But if I zoom back out and then I go to default preset, now we can see the moons. All right, those are coming out here. Um, and this is where you'd want to go to Stellarium and zoom in. And I go to the information over here, and that's going to tell me what I need to know as far as, let's see, I can move my bar over now. I can't move this over very well. Okay, I'm gonna have this screen I have a little trouble opening Stellarium, but we can see the information over here. Start Julian, there's a Julian time, center time, that's probably what you want. This is at Greenwich mean time plus 0, so there you go, okay. This one I did get down in Chile, so that's so Toyoyo, and prompt 6 is good scope, has all my information there. But yeah, that Julian date, that's what you really want to make sure we have. And you probably could be consistent and just do the start or the end center, but I think at the center time is what I stuck with, I think, on this one. Oh, wait a minute. You'd have to actually do the next one. This is the center time is not Julian date. It's the next one, the 24/6/09/77 number. Okay. And in this point, we have some really neat tools we can use. I'm going to go back to the eyeball. And by looking at the saturation levels, you can get it to where it is like you like it. And you're getting it a nice pinpoint moon. And I think that's one of those things that's just up to you as far as what you want it to be. There. So maybe I like this, and maybe I'll go a little bit farther because I want the Jupiter to be a nice central object. So I'm going to take this down. I'm not sure which one's Ganny. Ganny's huge. It could be
And
this one out
also,
here.
yeah, and also sometimes might be some of these moons are very close to the edge of the circle. That helps if we do it, play with this as well. Yeah.
Yeah. So I go over here now to these other options. We have custom markers, which are really nice. Custom markers, when you do this, you do centroid clicking. And then what this will do is kind of help you figure out that doesn't look like, let's do that. I should undo, I don't think I can undo that either. To click beneath, how do I delete it? Is it gonna let me do it?
I think you click again the icon,
I'm gonna come back.
the one that is centroid. Just click it again.
Oh, there it is. You get that one out.
Yeah,
Okay.
delete it. Okay.
Thank you. Okay, so I'm doing centroid clicks. I should be using that, I think, for this one over here. So let's say this is Ganny. I don't know which one's which, but I'm just going to use an example. Whoa, sorry, my bad. Let me pull this over. I just don't want to accidentally put a centroid on this if I don't have to. So if I click on this one, okay, now we've marked that one. And then for planet centroiding, I believe that this will see it. It looks off-center to me.
Yeah, it is off center. I think you have to click it first, delete those one, and click it first and stretch it the mouse to get the distance. Delete it.
Oh, okay. Yeah, I think you're
And
right.
I think unclick it again, the centroid click and the one that is on the top, this is blue.
Oh,
The
this
center,
one here.
yeah, do it and delete it again. Oh, it's not showing.
I must have put a bunch of them on there. Oh, there it goes. It's gone.
Yeah, it
Okay,
goes. Yeah.
let's try that again. Yeah, it seems like you could take this and you stretch it out, right?
Yeah. You have to click it, make sure that you do it when you do the marker for the planet, make it centroid click and both of them, you redo it again, but start from the moon and to the center of the Jupiter.
Okay, so I got this one. And then you're saying go back to Jupiter. That looked
Yeah,
pretty centered the
but
last
but you have to click again to centroid click. You didn't mark it.
on Jupiter.
No, on the up on the right, custom marker. Uh,
Oh,
delete that one. Go to the specific. Yeah, both of them. Yeah, both good. That's good.
okay.
Right now, start with the moon
Yeah, I got that one first. I guess it's
and
also redundant.
stretch it to the center. No,
Okay, yeah, so let me do that.
it's
I thought also, yeah, you could resize them. I thought that was in there. I'm
yeah.
not resizing. Oh, I know what it is. If I click on
You'll
this
find it.
one
Yeah.
here, I'll click there, and then I can resize it here. Okay, here we go. So I can actually, there's the radius, label radius, X, Y, all radius is here. So this one I can make it bigger. And oh, it's looking pretty good. Okay, it is centering as it goes, it looks like. That looks better. Okay, it has a little adjustments X and Y. So now I've got these two marked. And I do think when I go to the next part, though, I think it actually goes away. I always like this feature here. This is one where you can click once on the image to set the measurement start point and move the mouse, click a second time. So here's a way we can actually measure distances on Afterglow. So I click in the middle of Jupiter and I come over here and you'll see how I've got a couple things going on. I can
It's
actually
a heat
whip.
map, just like JS9.
Yeah. What? Like DS9?
This is basically showing like the intensity per pixel length, per pixel, like along the length of the line, correct?
Yes, and I'm going to show you what I like to do. So we could just measure straight to it, center to center, and get the distance. And that actually works pretty good. So it is actually giving us how many pixels over things are, and that works. But another option is you can click and drag across both of them. And if you look what's going on here, now to come over here, it tells me where the peak is here and where the peak is here to allow us to get a nice measurement of how many pixels over there are between the two objects. Does that make sense? And I think that's a little bit easier. I always, when I first started doing this, I was going center to center, which I think works great. But if you stretch across, you get a nice curve for this. And the only problem you might have is if the object itself has ununiform brightness, you might offset the center a little bit. And this one slightly does. You can tell it's a little bit off center. But see, I can find this edge here. Better way to do it, you find the edge on one side, you find the edge at the other side, and you find the midway point, and then over here you kind of do the same thing, and that would give you perfectly where the two midway points are, and then you can get your distance, which would give us very low margin of error on this. Okay, so it depends how much time you want to spend on it. For this exercise, you don't have to be quite that fancy. If you just drew the two stretch and you get the distance in, that's going to work really well for the exercise. You just want to make sure you got the right moon every time you're picking Ganny as you go through each day. How are we doing? All right.
I've done this before in JS9, yes.
Okay. Well, awesome. Okay. Very good. So let's see where we're at. So I'm gonna head back to the lesson, and I'd have to take a bunch of measurements. A bunch of measurements though, and when we get into Astromancer, it would allow you to upload in the options it has there. Let me see if I actually can open. Let's see. So it says go into Astromancer. I'll go ahead and open that up. He does have a nice tutorial on how to do this. I kind of like the Ultimate. The new tools are nice. And I'm trying to remember which one we pick. I believe it is the moon one we have here, where we click on this and then we can look at the data and look at your options you have here. Like I'd like to just stand back a little bit and look at the dots and look for a pattern in them if there is any. And then what we can do is adjust period, amplitude, and phase to try to get these to line up with each other. It looks to me like this one looks pretty good, but if it is very good, we have a problem that this one is not coming in soon enough, which suggests that we've got a period issue. So I might pull this in period to see if that doesn't help me out a little bit. All right, and it seems like it helps out, but maybe we have an issue now with the amplitude. And by playing with these parameters, there's phase is also in here too, so you can slide it side to side. You can work with period. You can work amplitude, surprisingly, is very helpful sometimes to finding a solution. You wouldn't think it would be, but it really is. But between these, then we can try to catch as many points as you can. And I'm not saying that I like that a whole lot. But I'm not saying that the data that's in here is any good. This actually might be my old data too. And
Yeah,
I'm not being
yeah,
very happy about it right now.
yeah. Might be, I think it's best that we see which point is the highest in the curves. Probably we get closer the highest point to the peak, one of the peaks, and then play with the period to see if we can make it very closer to sign like that. Yeah, and
Yeah.
then play with the period.
See, it can't be this. That's too small unless it was happening like that, which
No,
I
no,
don't,
no. It's
no, no,
gonna be,
no. I think we're out like this.
yeah, it is, might be a little bit more.
Yeah.
Yeah, a
Yep.
little bit less.
A bit
But
less.
the problem is that we have down there, there is few point. I think this may need a few way of, as you mentioned, to play with this to
Hmm.
see if it is work. And also, the another thing is the tilt. Tilt down there, we can
Oh,
play with the
yes.
tilt.
Very
Yeah,
good. I
it
forgot that too.
tilt,
That would make it
tilt.
interesting.
We have to play with these four bars to make sure that we put almost all the points on the plan. Right now, probably you change the phase.
See, I
Uh,
think when I did this, I think this might be some old data I had where I mismatched it. I don't think that these are both from the same thing. I think I have two different data sets in here. So as we're
yeah,
doing this, I need to clean mine up too. I don't have a good set of data, but through your observations each night, you can check your Julian dates, check your angular separations, and then those go in here. And this will allow you to make a nice plot. And from
right.
this, we can determine what is the period of this object going around the central object. And
One
uh,
question, John. John,
yeah,
is that two line? I don't see it. Line 5 and 6.
yeah, that's what I'm
There's
saying. I think it's two different data sets, and I hadn't replaced them all. I think I did a copy paste error where
okay.
I copy pasted like this the bottom half from another study, and I didn't delete out the first half, and I hadn't got it all filled in. So
Okay,
my guess
that
is we can probably
makes
match
sense.
these. Yeah, we can match the first ones, but we can't match these back ones because I don't think they go
Exactly.
together. I wonder if I don't move the phase up. See, that doesn't look right. I
Yeah,
can have a
no.
hard time matching those.
It's like
Uh,
the setter arc here from between point three and like the third last point, the peak it's sort of tilted towards the left, and the period is noticeably longer than any other peak.
Yeah, I think this is a different object. I think one is Jupiter, and I think the other one was either Neptune or Uranus, possibly. So they're not going to match up the same at all. But see, and remember for curve fits, um, ideally you go through all your points, but you're not going. That's actually not ideal. You should have a little bit of play. We're going to split the difference as you do it to get your best data. All right, so I'm going to be rerunning this myself, and as I'm doing that, I need a good set of data for class, and I have plenty of images of my own to analyze. But that's all I'll work through this next week is try to drop those in for Julian dates, and it does take some time in Stellarium. You'll have to go back and forth, but you get a process going, it can go pretty quick, and you know what you're doing. So, but the process, does it make sense for you? Good, good. Okay, so we head back here. So once you get this, and we can load that up as far as what you have and see how we're matching it. So we're looking for amplitude to period. Um, and do notice here, and this is really right, that you've got to watch your period, that it's a complete, kind of like a sinusoidal complete cycle. I believe it is two bumps, right? So record the semi-major axis A in arc seconds, and then you record the orbital period in days. And from this, we can actually move forward to the next part. Okay. So next you convert your measurement of semi-major axis to arc seconds. Let's see. So if we go to Neptune, you can actually find its distance from the sun here. It'll be in Stellarium. And you'll need to find that for the calculations. And like Jupiter and Saturn the same way. Saturn's going to be about 5 AUs. Jupiter is about 5 AUs. Saturn's about 9.5, 10, about 9.5. And then the others will be at 20 and 30 AUs approximately for Uranus and Neptune. But you want that number exactly if you want good data on this. And then at that point, yeah, I do. Oh, yeah, that's a good thing. Use distance, not distance from sun. So do be careful there. When we work this out, right? Because we're making the observations. Boss, is that
Yeah,
because we're making the observations from the Earth and
yeah,
not from the
yeah,
sun?
yeah, from the Earth, because we're taking the pictures and measuring from the Earth. Therefore, we have to check it based on the distance, not distance from the sun, because there is many data over there as stellarium exists, but because doesn't matter which part of the Earth we are looking, because the picture is taken either by from Chile or from Poland or Moorhead or any other places. But all of them, we are assuming the Earth is 1 point, and the distance that parameter of the distance in the stellarium gives better indication about the item we needed on this lab.
Yeah, it makes a lot of sense. It's just a small difference on the Earth for distances
Yeah,
that have
yeah.
a great distance.
We ignore that. It's actually Earth has we are not on the center of the Earth, and every place is different. But I think from that point of view, it doesn't cause any major the reason is that distance of the Jupiter or Saturn from us is too large. The small changes on the diameter of this Earth, it doesn't cause any major problem on the measurements.
Yeah. So I'm thinking, so my physics knowledge base, there's little that I have, right? The radius of the Earth is like in the millions of meters, whereas the distance between the sun and these objects between the Earth is like 10 to the 11th meters. And so we have many factors over. We're very insignificant. We're a point in this problem as we go forward. Now, I do believe we've talked a little bit about parallax. I think you're a little aware of what that is, about how the angle, right? You get distances from angles, and that's really a lab 4 item, where we'll get into parallax, which is very cool. But from this length does correspond to an angle. So lab 4, learn how to measure distances. Make sure I'm not jumping ahead of the gun here. Just a little bit of parallax. We've seen it here that the farther out you are, that angle does correspond to a larger length. And this is the thing, like a little plane up close looks the same as a big plane out farther away. You have to do a little bit more to figure out how far it really is. Okay. But from the angle, if you do have the distance to the object and you have the angle, and then we can use this ratio to figure out how big something is. Okay. So that's why that angle is so important, to figure out how much angle has subtended, and knowing how far something is away. So 2 pi times the distance, that gives us a circumference. And think of this length here as being part of the whole circle. Always think of it that way. The ratio of that little piece to the whole circle is the same thing like our little angle to 360 degrees. The ratio works out spot on both ways. They're comparable to each other. And so by using that ratio here, there's our distance, there's our length. I mean, we got the size there. We've got the distance, which we know from Stellarium, and from that angle, you can actually figure that out. So using this equation, you should be able to figure it out from your arc seconds to AUs, figure out where this is. Oh, a little note then. So there's how many arc seconds in an arc minute?
60?
Yep. How many arc minutes are in a degree?
60?
And how many degrees are in a circle?
360.
Those Babylonians love 60. Very popular number back in the day. Okay. And how many legs are on a cow? No, there you
Five.
go. Just kidding. Okay. But anyways, yeah. So it kind of plays in here. And do keep your precision in here. I keep a few sig figs. You're going through this. Um, and it should be very small. Yeah, AUs are huge. I'm expecting the size to be very small, but it's doable, which is very cool. Keeping your precision, you can get some really nice values for the size of our object here, of our planet. And it's amazing to think that Jupiter is even a fraction of an AU. It's actually noticeable. That's pretty crazy. We got a little cheat sheet on here for us, and we're just basically continuing on with the same process as you go forward to get ourselves to years. And then by this ratio of solar masses, kind of jumping through this pretty quick, we get the mass of Jupiter out of this from all this process. So keep going through the steps. And then like next week get stuck or anytime, let us know as we're going forward. But you should be able to figure out the mass of Jupiter. And Jupiter's big. It really is big. I love the newest astronomical research, which has been pushing down how much mass it takes to turn into a star. Jupiter's not there. It's not there. It's down, I think, by a factor of 20. I think I heard last, was about as close as it gets possibly. But it puts off good infrared, but it's not going to light up on us. Um, and Uranus and Neptune is surprisingly, I think, pretty close to Jupiter in mass, which is kind of amazing as you go through that. Okay, so then we can convert that to Earth masses, and that's going to become big again. The numbers come up, and if somebody wondered how did you mass a planet, now you know how to mass a planet. Okay. The last part on here is Venusian phases. And I'm looking at our time, boss. We're at 9 o'clock. So should
Yeah.
we kind of pull it to a halt here?
Yeah, I think we halt here and we keep it this for the next one. Thank you, John, for helping on this session. It was very great. And also make sure that Ron, and also I'm gonna send the email for everybody for after recording. Make sure that 14, I send on the email as well, that make sure that this 14 images starting as soon as possible, because if
Got it.
you just late, it's gonna take 2 weeks to get the result. But at the same time, as John and I mentioned, as soon as you get the first or second image, you start developing the result on a spreadsheet back to back. And then as long as you go that, you can do it repeatedly, use the Astromancer to get the graph and see how the P and the A is developed. And that's going to be also helpful for you when you do, if you keep it by the last time, the 14 days. After 14 days, you may do it once or two, but if you do it frequently, check it, you will learn more. Uh, I did it myself, I learned more. Because of that, I'm trying to engage you to do the same. And therefore, that's gonna keep in your mind and you never forgot. And that's one of the key things on the lab, engaging and also hands-on activity. When you do it more frequently, you learn better than the one to do once at the end of the 14 days. And and if you encounter any issue, and also I'm just guessing, John, probably we have some idea, or Rohan, if we get an idea, if all of us in the session, for example, we have 10 or 11, if we ask for each of us get the number based on the mass of the Jupiter or orbit of the moon at Jupiter and compare the kind of statistical to see how much we are close calculation to each other. That's going to be also a good scientific activity in a class that we do the same thing with different individual with different results and manipulating the different values, and that's going to create very good scientific article if we need it to publish. And that's going to be a good thing if everybody agrees, or at least 5 or 6 of us we can do that. We can collect the material very good.
Yes.
Yeah, we probably need to do so. Ron, remind me, we can do is try to bug some of the others we run into them at school. A lot of them I don't have in class, and so we'll try to get a hold of everybody else too to try to take them through this. Some of the guys I'll see in astronomy class, I'll say something to them to try to get their observations going and help them get through that process
Yeah,
so that we can get this rolling because it does take 14 days to get with the full set of data.
that's
It's a
right.
little
I'll send out a message in the astronomy group chat we have, though. That's just Aravind Vetri, though.
yeah, and yeah, Arv wasn't in
Good
class
idea.
today either. I saw
Yes, he
Vetri after
wasn't here
school.
today.
Yeah, I should just say something again to Vetri after school. So I did see him. Um, so he must not be feeling good or he's out of town, one of those two.
Yeah.
And I'll see
Okay.
one of the other couple of guys next couple of days.
Very good. Very good. And hopefully that you get a good result and good thing. That is one of the, I will say it, I like it the most. One and two is more close to the earth, and one is the basic lab one, basic of the learning. But I think when we go to the lab three that we are, and lab four and lab five is a meat of the OPIS. And we're gonna get how, how amazing that with this tool you can measure the mass of the Jupiter or mass of the Saturn or mass of the planet and also distance of the moons from the planet. And that is not things that you can do it easily in last 50 years. And that is things that is electronic and also the SkyNet and the facility remote observation create a very big tool and effectively we can do it like a professional astronomers 100 years ago.
You imagine that you'd have to set an alarm every day. You'd have to put a film canister on it, load it up in the dark, put it on a camera, and hit that button at the same time every night and hope it wasn't cloudy where you're at and hope you actually got a picture of it, then develop it quick. And it'd be a process. So yeah, this
Very
is so
good.
much nicer.
Very
Yeah.
good. Glad to see you. Any other last question, Rohan or John, you may have add anything?
Now, also
No,
there's a
okay.
meteor shower in a couple weeks coming up, and the
Yeah, yeah,
planets are starting to come up at night, so it's a very fun time right now.
yeah.
I think
And
that
I,
it's pretty interesting. There's a lot of overlap between this course and what we went over in astronomy prep for Science Olympiad, parallax specifically, and yeah, Astromancer JS9 similarities.
So you should have
very
such an
good.
advantage. I want to see you on that stage at State for Science Olympiad with that medal around your neck. That's what I want to see. All right.
I hope so.
I hope so too.
Thank you. Thank you, everyone, and I wish you have a good night and see you on next Tuesday.
See you next Tuesday. All right. Night.
Bye bye. Have a good one.
But
Bye.